Ya estamos, ¿no? Bien. Hola, ¿qué tal?
So, hello, everybody. Good afternoon. I've been already introduced. My name is Danielle. You probably know me because of my nick Adastra. I'm the author of the blog thehackaway.com. I am author of several books, including one called Deep Web Privacy and Anonymously, and then two on Python, Hacking with Python and Python for Pen Testers. I work with pen testing. I am also a trainer, and as many of you, I do this out of passion, out of love, not just because I make a living out of it. So what am I going to talk about? I'm going to talk about several basic concepts of TOR and Freenet, two very different solutions. I'm not going to talk about basic concepts, as I'm sure you already have a certain knowledge. After that, I will talk about several techniques we can use in order to attack users using these solutions. I have to say that I'm not going to talk about zero-day vulnerabilities. I'm going to talk about techniques that are applicable in order to break the anonymity of users using this kind of applications. Therefore, this talk is going to be highly technical. So we're going to talk about the general functioning of TOR and Freenet, basic concepts. We will talk about detection of vulnerabilities, pen testing, and exploitation of hidden services in TOR. These are services that may be exploited as any other service we may come across in the internet. We will talk about the replication of hidden services, the creation of decoys in TOR in order to reach hidden services that include malicious routines, enabling us to attack the anonymity on the user side. We will also talk about the creation of malicious complements without verification from an instance. These two last points will be focused mainly on Freenets, which is an anonymity solutions focused on the content distribution. The focus is a little bit different, the approach is a little bit different from TOR, and so are the attack techniques. So how does TOR generally function? Well, this is probably something you know and you master. You probably know the basic concepts. TOR is a network that provides good levels of anonymity thanks to a distributed network and the internet that uses a TOR protocol. This protocol enables us to use the TOR network and export all the packages to a particular destination. It can be used in out-proxy and in-proxy modes. Both of them are very different from each other. Out-proxy is about surfing on any website, for example, Facebook, which is very good for your privacy, by the way. And you can use TOR in out-proxy mode in order to reach that kind of service on the internet anonymously by using the infrastructure provided by the net. Then we have the in-proxy mode. This is a little bit different. The way it works is different because we are not accessing services online. We are accessing services which are inside the TOR network, and they are made up of an onion address. You've probably heard of that. So this solution has been on and out the market for many years. It's being developed since 2003, more or less. And as a result, the TOR community is pretty big. It is stable, robust, and it has a long trajectory that gives proof of its quality. You've probably seen this picture before. The most well-known personalities in the cybersecurity world. You've probably heard the names of Alice and Bob in cryptography. So this picture that was taken from TOR's official website explains how TOR works in out-proxy mode, how we navigate towards an internet service. Alice here is the client and wants to connect Bob, which may be an internet service, typically Google or any other website. So what does Alice do? Alice uses the TOR network and it requests 3 repeaters, an input, an output, and a repeater. And this way it enroutes all the packages throughout all these repeaters. This is the classical out proxy model that you may know. The advantage is that the output mode removes the last encoding layer of the TOR protocol and sends the package to the destiny. So if we don't have an additional layer to the one that TOR provides, we're going to be in trouble because the packages are going to travel in plain format.
Todos sabéis, ¿vale?
In the in-proxy mode, in TOR, things are a little bit different. Here we can access services that are within TOR's deep web. These are TCP services, and they cannot be UDP type. So TOR only enroutes packages of the TCP protocol. In addition to that, we don't have a DNS resolution, which is very typical in the Internet. We usually use DNS in order to solve directions and addresses. This is not like this in TOR. In TOR, we have addresses which are .onion. These are text chains with characters from A to Z and numbers from 1 to 7 and a length of 16 characters. This is the way all onion lengths are, onion addresses are. So what happens in this case? It is more complicated than before. In the out proxy mode, we saw a circuit, 3 repeaters that the packages travel through, and then they reach their destination. In the in-proxy mode, that is when we have hidden service that we want to query from an onion address, there are many things to bear in mind. As a matter of fact, all these green lines you see here stand for a circuit. So we have 3 repeaters here. So to summarize it, the ultimate goal is that the hidden service and the client are anonymous to one another. So they respect anonymity towards the service and the client. Therefore, clients and services are both anonymous. These green lines, as I said, stand for a circuit. So what does the hidden service when we create it? This is very simple to create with 2 configuration directives that show that there is a hidden service in our TOR instance. So what does the instance automatically do? It generates a descriptor that contains everything necessary so that a client can access us through an onion address. This is registered in the DHT, which is TOR's database. In this database, we have all onion addresses and their HSD, hidden service descriptor. This is what we typically find in our HSD. So the client queries an address in DHT, and what it gets from DHT is the corresponding HSD. So this way they have the code to encrypt the data package and an introduction point that is represented by an onion in the middle here. So the client selects one of these three introduction points and sends all the packages that way. So TOR knows where the destination is and how to get there. All the data packages are encoded with the key that was in the HSD. This is a bit complex, I know, but this is what TOR is about. Before taking all these steps, the client chooses a repeater online in a rendezvous point, and a meeting point, so to say. This is the most important one. It's the meeting point that all the packages are going to go through, and it's the node that will enable the communication between the server and the client. So the rendezvous point generates a secret, so to say, a key that is sent to the client. Then the client connects to the introduction point and is sent to the hidden service. So from that OTC and the address of the rendezvous point, they create that connection. So this service sends the OTS. The rendezvous point knows that it corresponds to a service. So we have this communication that is made up of two different circuits that are independent from one another. Anonymity is a lot more solid this way.
En la medida de lo posible rápido, y os recomiendo que le echéis un vistazo a la charla de Fran y de Manu del año pasado en este mismo evento.
In the same event in CyberCamp, speaking up with somebody that spoke about TOR last year, last year's edition. So I recommend you to take a look at it in YouTube in order to have some doubts clarified. And now let's speak about Freenet. And Freenet is an anonymity solution other than TOR. With TOR, we find that we have an HTTP server, etc., whatever service you want, as long as it's THP. In the case of Freenet, there's no service. In Freenet, we have content distribution, document distribution, all type. You may distribute it through the Freenet network. It's a P2P solution from 2001. It's one of the oldest anonymity solutions that exist. And unlike TOR, this is a network that's absolutely decentralized. It means that in the case of TOR, there are some directory authorities that control the whole net. In the case of Freenet, nobody controls anything. In the case of Freenet, any instance may share documents, contents, etc. with whoever wants to access their contents. The only thing you need in order to access Freenet is to have the corresponding password in order to access that content that we're going to see right now. There's an important thing right now with Freenet, just as in I2P, it's not like TOR, where you may select whether you want to act as a repeater or not, or rebooter or not. In the case of Freenet, you always share it. You're always a repeater. In the case of 2P, same story. You're always going to be sharing content. And this has its good things and bad things. A bad thing that could be quite bad is the data store. Freenet is based on a distributed data store space where all the contents you have in your instance are stored and they are encrypted, and you have no control whatsoever on everything that's stored there, no control whatsoever. In your hard disk, there may be malicious contents, illegal stuff, and first of all, you don't know about this, and second, your computer is being used in order to store things that you don't know about. You don't even know what is being stored. So in fact, when you go into the Freenet official website, they tell you about this, and they say, hey, careful, this is how the network works, this is how Freenet works, and you have to take this in to account. And in a case where a three-letter entity may wish to break into the encryption of your data store, if they find any malicious content, you may speak of a plausible denial, because actually you don't know what is in your data store. So this could be true, and this is what they advise you to do in the Freenet project. This is an proxy solution. In this case, a connection with external nodes to the network is not allowed. There's two operating modes, the OpenNet and .NET mode. This is interesting in the case of Freenet. When we set up Freenet and we start playing around with it, we always work in the OpenNet mode. We connect to any repeater in the net, and we can use them in order to take a look at keys inside the network. This is OpenNet. But when we speak about .NET, this is a different story, because we just connect to nodes that we trust, repeaters or other instances in the Freenet net that we don't know, that we know present no problems. That is, we trust them. Imagine that in a university you set up a .NET group of friends, and this .NET you share content. Everything you share in that .NET will only be available for users in that small group. This content's not gonna get out. That is, no instance, no node will be able to look at a key or a password.
Vale. Esto puede ser un problema. ¿Por qué motivo?
This is a problem. Why? Because there's a problem related to people who may want to share malicious or illegal content because there's no way to find them. In this case, it's not an OpenNet mode. In this case, contents are shared inside a small group, and this is difficult to handle. But nowadays, the safest possible node in order to share information or documents, that is the .NET mode.
Bueno, esto ya lo comenté antes. Todas las instancias de Freenet cuentan con su propio data store.
And here it's got its own data store that can be configured. Here you can, for instance, how much hard disk we want to share, what the size of our data store is going to be, and we can also decide whether we want our instance to work in .NET node, and to this end we need at least 5 friends. We can add friends contacts. If we have 5, we have 5 friends. We can set up .NET. So we need at least 5 friends. And another thing, Freenet is resistant to censorship. It's something that can be achieved in the case of other solutions like TOR or I2P do not allow for this. We have a hidden service in TOR network, and for whatever reason your computer crashes or you switch it off, the instance is outside, so that service is no longer available. But in the case of Freenet, if you upload a content to Freenet and somebody looks at it, that content will be available in your local data store and in the data store of the person that looked at it. So if the computer switched off, that content will still be available with the same password in another repeater. So if that is downloaded by several repeaters in the network, this is going to be quite difficult to censor it, very difficult to censor it. But the system of Freenet is based on the amount of times that you access content. If content stops being accessed, it disappears from the net. The data stored starts clearing, starts being cleared in order to leave room for other content. So therefore, this is a system that's very interesting, resistant to censorship, and like I said, only contents that are popular will survive or will remain accessible, available with certain regularity. And when we work with Freenet, one of the most important applications we have is F-Proxy. F-Proxy is an application that allows service in the 8282 port, and we can access it through engine. We can configure complements, or we can upload or download files from Freenet. So these are characteristics we find in any Freenet instance, and we find other things like Web of Trust, Flock Helper, Freemail. What these are documents you can use in order to make a Freenet instance more lively, because it includes very few things. If we start adding complements, then we have the possibility of having anonymous identities, email, and things that look more like a solution based on services, even though we still have a contents-based solution or distribution-based contents. Passwords in Freenet are essential in order to access contents. We have different types. We have the CHK, 55K, USK, and KSK. When we want to upload content that's not going to be modified frequently, for instance, a document, some sort of a document that you know is not going to go through changes, or an image that you know is not going to change. In that case, you use a CHK if it's a content that you expect to change every once in a while. Then we use a double SK or a USK, because here you have the possibility to have two versions. The same content may be included in two different versions. If we update the content, then the version is updated or goes up. It's like Subversion or CDS is a content control system, very similar. In this case, these passwords or keys are an encryption key, and if you know this key, you can consult it in the Freenet net, and some instance will reply and say, well, this key corresponds to the content I have in data store. But careful, the only way to have content in your data store is if you know these keys, or else there's no way to access that content. Okay, well, that was the introduction.
Vamos a ver, pues, un poco de pen testing contra este tipo de soluciones.
Now we're going to see what we can do with these solutions, or we're going to look at some attack techniques, which is what you're all waiting for, I'm sure. First of all, being a user in the deep network, any network, for instance, in service-based solutions, we find the problem that we find with any service in the internet. If this service vulnerabilities, we can attack those vulnerabilities, gain access, and if we gain access, we're there. We can know more details about who the user using those solutions is. This may sound complex, but it isn't. Actually running pen testing programs against services-based solutions. This goes through using test using a proxy. As we'll see, we can use I don't know, proxy chains, or we can use SOCAT in order to route all the traffic through SOCs, proxy SOCs, and send all these queries to an onion address. And what we do is map a port in our local machine, and all the queries that come through that port are sent to the hidden service as if we were attacking a service in our local machine, only with prochains, for instance. Everything is routed, as you may very well imagine. The advantage is that we can use all the tools that we already know, pen testing for web, pen testing tools in order to test the strength of an SSH service, etc. And that's the advantage that we have when we carry out pen testing checks against hidden things with this sort of solutions.
Sí. Bien, vamos a empezar con este. Fijaros, a ver. En este caso concreto, tenemos un fichero TOR RC.
In this case, we have a TOR RC file, a TOR configuration file, and we are creating several hidden services. Here we have a hidden service there and hidden service port combination. To create a hidden service, we are creating an FTP, HTTP, etc. We are going to run a simple pen test. We elevate the instance with this configuration file, no problem. The instance is elevated, and now we are going to use a vulnerable application called Django mode. We elevate it in the port 8080 that is mapped in the configuration port. So nothing new so far. We elevate the hidden service, we disclose it. Here it is disclosed, and the TOR instance is going to have an onion address linked to this service. Here are all the directories that have to do with each of the services that we've created. A private key and an onion address in the host main and the private key files. In the first one, we have the onion address for the hidden service. Each of them has its own address, and if the services have vulnerabilities, we can attack them, starting from their onion address. Of course, we need to disclose the service first. Here we disclose the browser as usual.
Aquí tenemos la dirección onion del servicio HTTP que está apuntando a Django.
So here we have the service pointing at Django mode. And we have a hidden service that has a web application below that is vulnerable because of its design, therefore easy to attack. This is a web application with many vulnerabilities that can be easily exploited. This is just a concept test, but hidden services with the vulnerabilities, there are so many of them, and we can attack them in the same way. Here we're interested in the onion address, and here in the port 9051, we're going to have the proxy socks elevated. So we use SOCAT in order to raise this port, the 7000 port in the local machine, and we indicate that all the requests coming in through that port are going to use a proxy socks against the onion address. The port is 9050, as you can see, and it is the one that the Tor browser elevates by default. So all the ones that go through the port 7000 are going to be routed by the port SOCs. Here we can see that the port 9150 is open, everything is clear, and we can very easily launch a NICTO, which is a very common application for pen testing. And we do this against the 7000 port, the local machine. All these petitions are going to go through the tunnel we opened with SOCAP. So we have access to the TOR net, and here we see the hidden service. So Django mode is thought for this sort of framework, W3AF, so let's use it. The only difference between attacking a hidden service in TOR's deep web and a standard service on the internet is that tunnel we have created with SOCAT in our case, but we could have used SSH tunnels or proxy chains. So here we establish the target. It is the local machine, port 7000, and proxy SOCs will route it to the deep web. We execute the attack with star. It takes a while because it all goes through the TOR web, but finally we find the vulnerability, and through that vulnerability we are able to execute the OS commanding complement in order to exploit the vulnerability, of course. So this is not really complicated. It is like attacking a server on the internet. The difference is that here we have a proxy that will enroute the petitions, the requests. Other than that, it is the same. We execute the attack, and now we can execute commands against the system. Here we have W in order to see the users who have logged in the system. So it's really simple. What is more complicated is to find the service that contains malicious contents, and then find vulnerabilities inside that service, a usual pen testing. So this is going to take very, very long. So let's move on. This is a way of performing an attack against a hidden service in the TOR web. However, we have other goals. It's not always possible to attack hidden services because some services are correctly secured. This happens sometimes. People who use this kind of solution, especially if they do it illegally, that is, when they use TOR in order to distribute legal contents, well, they are very much concerned about their privacy, but they forget about security. And we find many times hidden services with vulnerabilities that can be exploited and can severely affect the user's privacy. So, which are the goals? First of all, TOR Freenet and these solutions aren't conceived in order to cover or support cyber criminals. Their goal is to provide good levels of privacy for people who really need it. For example, people living in countries with restrictions where the most basic rights are violated by the government or other circumstances. In these cases, these people can communicate anonymously and without any censorship. This is the ultimate goal of TOR, not for protecting cyber criminals. However, these solutions are used also for the distribution of illegal content and for the distribution of things that weren't the original goal. So our goal would be to block hidden services with malicious content, to discover new services in the deep web with illegal or insidious contents. We need to be surfing very frequently because these contents are usually volatile. We can find the hidden service disclosed one day and closed the day after. So if they have illegal continue, we need to attack them as quickly as possible and also keep a log of them all. Control, even partially, the infrastructure of anonymous networks that don't have a decentralized model. TOR is centralized. We have repeaters, which are known as directory authorities, that control absolutely everything in the TOR network. They control the network status. So what can we do? We can do something that happens very often. We can try to overflow the TOR network with malicious repeaters that analyze traffic. This may be very effective in the out proxy mode because we only have 3 repeaters. Because if we have one output node and several input nodes, we can try to correlate traffic and launch several types of attacks in proxy mode. In proxy mode, sorry, this is not valid. This is only for the out proxy mode. Another thing we can do is to disseminate contents and publish content in the deep web that may give proof of the identity of the cyber criminal. We can create decoys that provide illegal services with the goal of trying to reach that person. In TOR's case, the idea is to create decoys. Can we talk about encouraging crime here? This is not what I'm interested in. I'm just giving you the technical standpoint. But you can consider that this is just a way to promote criminality. Drug selling or drug trafficking, people trafficking, pornography sharing, etc. What do we do in this case? Well, I don't know. Then the cookies and the storage elements which are persistent on the client's side. We can create malicious routines developed in JavaScript. Well, you can think, well, if I use TOR browser, there's nothing wrong about it. Well, no, because it has a very low security level that allows the execution of routines in JavaScript. We can edit the security settings between low, medium, and high. On the higher you set it, the more difficult it is going to be to browse. That's why when we install TOR browser, we can execute everything: JavaScript, CSS, absolutely all sorts of contents. So this is something that people can take advantage of. So we can clone hidden services with malicious or illegal features and then disseminate those services in the deep web. For instance, in this particular case, we disclose a TOR instance manually. The port 9050 is available, and we use TOR socks, which is a tool that enables us to enroute all the traffic from the console through the proxy socks of TOR. And in this case, we have, well, a service that sells drugs, weapons, heroin, speed, well, the usual shopping we do. Well, here we have the onion address, and what can we do? We can try to clone this service, making it look exactly the same. And how do we do that? Well, there are many tools, but wget is the most convenient one. Wget allows us to do a scrapping process against an onion address and download the contents. Here we are using TOR socks, so everything goes through proxy socks, and we download the contents recursively. All the contents that are found inside that onion address, all those contents are stored in the local equipment. So then we can disclose a web server, for example, Apache, so that we can have that hidden service cloned. They are going to look exactly the same. This is what we downloaded before, and for demonstration purposes, we disclose an HTTP server and the port 8080 with Python. Now we go to the browser, and if we go to the local machine, to the port 8080, we're going to find exactly the same because we downloaded it bit by bit. This is the local website, and this is the website in the deep web. It's a clone. The contents are exactly the same. So what can we do with those contents? We can modify them. We can try to introduce malicious routines. Let's say, well, let's see it in practice. We can introduce malicious routines that enable us to execute JavaScript, for instance. Now, it's true that some people may remember the onion address of this service if they use it regularly, and they will probably remember the same characters. It is very difficult that someone remembers all 16 characters, so we can customize our onion address, the one that we've cloned, and repeat the same characters with the same pattern. This one started by new blah, 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 and we can use a tool like Charlotte in order to customize the address and make it start by the same characters. This way we can customize the attack. We customize it and we distribute it around onion addresses, common search engines, etc. One of the advantages of TOR is that we are able to publish onion services very easily in most of the general search engines, grams, etc. Search engines that are common in the deep web. It's not like Google that penalizes our searches. Here we can register our onion addresses very easily, so we could try to disseminate these services. This is the interesting part. The service is cloned, so what do we do next? We try to introduce JavaScript routines that do something that enable us to have control over the users that access that service. So we start from the hidden service that we saw before with its onion address, and this is a bash script. And here we're going to do three things. We're going to disclose an MSGRCP service in order to feed it with a tool called Beef. This Beef service is going to be disclosed in TOR's deep web. Let's go little by little here. Let's disclose the fake service, the one we cloned. We're going to use Python to make it easier. Python -n/sh, and here we go. So when we run this script, we disclose the Metaexploit service in order to use it with Beef. And then we can see several things. The Beef instance is disclosed. Then we have TOR instance, which is also disclosed, and here we also have the MSGRSP service disclosed. So here we have something going on. We have a little infrastructure, a directory with the web services, the onion services. We have the onion address, which corresponds. Let's wait a minute because there is a lot of fuzz next door. So here we have the hidden service cloned. We have a JavaScript routine that corresponds to the beef hoop. So here are the hidden services. We are going to expose the cloned service and the beef service, the beef instance that we've disclosed. Now we're going to the browser. We will see the onion address for beef that has been disclosed in TOR. We go now to the panel, and here we can see beef's authentication panel. Are you all familiar with beef, with this tool? Good. Who isn't familiar with beef? Good. Almost everybody. Beef is a tool of exploit that is client-oriented. It creates a malicious routine in JavaScript that connects the victim's browser to the control panel. So from Beef's main dashboard, we can run different commands against the victim's computer. So what happens? We send the hook to a website. That website is accessed by a user, and the JavaScript routine runs, which is connected to our dashboard, to our CNC, and we've established a communication channel between the victim and the CNC. And from CNC, we can unleash attacks against the browser. We can run commands, we can make queries, we can do many things with Beef. We could create a new framework, we could include more JavaScript code and many more things. It's a very interesting framework that is client-oriented. So we have Beef as a hidden service, in our case, with an onion address. The hook corresponding to the JavaScript file, it is inside the hidden service we have cloned. I don't know if you saw it. The index website of the hidden cloned service had the script, the onion address /hook.js. So when the website is loaded on the browsers, there are going to be requests against our CNC, and we from our CNC we will be able to send commands and disclose the client's anonymity. Here we authenticate ourselves in Beef, and we can see online and offline browsers. This is a dashboard. Well, the colors, well, you may think they're nice. I think they are dreadful. But anyway, here we have the onion address of the hidden service for Beef, and we have another onion address corresponding to the cloned hidden service. They both look the same as we saw before and on that website that sold absolutely everything. So here we have the address. We load the website, and what happens? This is what the user is going to see. It may take a while. So he's going to see the exact same page. It's not the onion address that we saw in the beginning. It's a different one, but they both have the same content. And here, as you can see, there are requests being run all the time against BEEF, against CNC. We have the dashboard connecting to the browser at all times. And here we have the browser hooked. Here we have we can see that it is constantly running. Here we have the address. So from this browser that we have hooked, we can start running different sorts of attack. We can see, first of all the information from the browsers that we have hooked, and then we can run commands directly against that browser. Here, for example, we have detect Foxit reader, very simple commands trying to collect information on the victim.
¿Qué más cosillas? Tenemos en Chrome Extensions, bueno, tenemos un montón de...
We have Chrome extension. We have many different available commands and complements. BEEF is complement-based, and its advantage is that we can do absolutely everything with it. We can generate a notification bar, a fake notification bar, the kind of thing that pops up when we are browsing through Danko series and other websites that have online series, and they ask you to install Flash complements, for example. Here we can do exactly that. We can make this message pop up, and we've launched it directly from BEEF. We could use Uniframe, we could redirect the user's browser to a different place, so here the user is hooked. And we can also run a cross-origin scanner in order to scan the internal network of the victim, as long as we know which network segment they are in, a LAN in this case, within a pretty usual range that you can see on the screen. When we run this, BEEF is going to send requests against port 80 and port 8080 and different IP addresses against port 80 and port 8080, as I say. Here we can see if inside the victim's network there is another disclosed computer which has one of these services active, thanks to the port 80 and the port 8080. This may take a while. Scanning takes a while, of course. This is a very powerful tool, and as we can see, we can hook it to an Onion service which has its own JS instruction. This is what I was talking about before. In the configuration details of the web browser, we're always going to have a low level by default. Every time we install TOR browser, that browser, although it gives security its importance, by default will have the low level set. So you can run any type of routing, including anything from JavaScript. A couple more things. Well, now we are going to move to Freenet. Freenet isn't service-based. It is an anonymity solution that is based on content. So a good way of trying to compromise somebody's anonymity is to upload malicious content. .exe file, .f file, and maybe with social engineering techniques we may have the user execute that kind of content. It is a bit more complicated, but it can be automatized, and we can see much improvement. Here we can use MSF Venom, for example, in order to generate a malware sample in the ELF format. Here we can generate a file, a payload with the ELF format that we can upload to Freenet from fproxy. So here we have the possibility of uploading a file using a canonical key with a random key as a CHK in this case. Here we insert the file, we wait a few minutes until the file is uploaded, and when it is completed, we will have a key once the upload is completed. So if you look at the last column, you're going to find the CHK address, the address for that content, the address that leads to that content. And if it is a Freenet binary, you have to be careful because you may download this, run it inside your computer, but it may be risky. If you still want to go ahead, click here. So this kind of content is blocked by Freenet. Freenet detects it's an ELF, it's a binary file, and warns you, tells you not to download it. We could do the same thing with other run files. For example, in Windows, with PE files, the .exe files. What do we do in this case? We create a template that will be a putty.exe, and from that template, we inject in that software the malware that we want to distribute. We generate the .exe file, and we can upload it as a CHK key. Then that key may be distributed across the network, trying to encourage people to download it. Of course, here we have to apply social engineering techniques. Well, of course, this attack vector is complicated in the sense that, well, how many of you believe that someone is going to trust a run file downloaded from Freenet? How many of you would download a run file from Freenet and install it? Really? Well, you are a troll, aren't you? No, trolls are actually this way. Well, obviously nobody or almost nobody would download a run file and launch it and open it directly inside their computer if they downloaded it from an untrustworthy network such as Freenet. So how can we make the user download that sample so that it runs inside the computer? Well, as I was saying before, Freenet gives us the opportunity to run complements. These are routines that extend the capabilities that Freenet already has. So one of the advantages that we have is that we can create our own complements with the API of Freenet. We can use it in order to create all sorts of complements. We can develop the complements ourselves. Of course, we need to know how to program, and then we can generate a .har file, distribute it, and with the use of social engineering techniques, we can have users installing that complement. That is probably easier to believe by users. Imagine, for instance, a darknet. That, as I explained before, is a group of people that share contents in a closed circle. Imagine that dark net distributes child pornography content. To give an example, so in that alleged dark net, we can tell the people who want to access those contents that, okay, you want to access our net where we're distributing this kind of files, child pornography pictures, for example, you need to install this complement. This is the way you're going to gain access to our group.
Social engineering techniques. The idea is to trick or to sell something to the cyber criminal that he may sell. Installing a complement could be much easier, much more viable, and it's a much more credible attack vector. So let's see what this looks like. Okay. First thing is what I was telling you. We have the Freenet based in Java. And here, in this case, we have a plugin. It's a type of Java implemented by this Java interface. And we have a plugin respirator that allows us to control the details of our instance. We say run plugin, and we create a trace file, and this is something that can be removed. But the interesting thing comes later. Here, after the object, we can obtain a reference of the node, the plugin respirator. For instance, here we can get the name of the node, the shared band width, and here also when we obtain Freenet. Oops, hold a second. Here what we do is to create a URI key that was going to respond to this CH key. And we've created this, we've put it with Freenet, and remember that these keys can be downloaded by anybody. In this case, we're going to download them from a complement using a URI Freenet and the corresponding client. Here, what do we do with the client? We say download this URI, this key, and then you create a flow and input stream in order to read the whole file. This is a and we put it in a temporary file called shelf.elf, and this is something we're downloading on the local machine. All this is being run in the victim's machine, or the potential cyber criminal. And here what we do is basically to save everything in a temp file, and using the run temp of Java, we can use this get runtime and to run that .elf. And what does this do? It downloads a key that we've already uploaded to your Freenet, and then it runs it. Basically, this is what it does. It downloads the content that corresponds to this key. This is a malware sample, something that we created, and that is run. And this is the only thing it does. There's the manifest. These are details. Here we can generate a hub, or from command line we can use this command, and then what do? We tell the user, the potential victim or the person we've asked to install this complement, to do it directly from their Freenet instance. And here we have the possibility to install complements of a Freenet or developed by a third party. Configuration, plugins. Here we see some plugins that correspond to the instance, things that already exist within Freenet, and we can tell it to install an extra plugin, a non-official Freenet plugin. Sold by a third party, three alternatives from file.hard or from a key chk. Any is valid. In this case, we're going to use a .hard, but we could give it a chk key. And we also have a meta-exploit. Remember that we generated our sample with meta-exploit. And here is a handler and the corresponding port. We run it and we wait for it to connect. The payload is Linux, blah, blah, blah. The options are already there, and exploit. And we wait for a connection. And when's that connection going to happen? When the plugin in the Freenet instance is run. And it's going to be run when we load it. And when we say load, the the run plugin method is executed, is run, then we have a CHK key downloaded, and then the program is launched. Here we have to wait a little bit, but in the end we have this meter session, and we can do several things in order to have a pederast install it and thus chase him, catch him. And what we need to do here is two things. The initial attack vector, what social engineering is going to be, and on the other hand, we have to work on the plugin. And these are the two things we need to work on, but from a technical standpoint, what we saw here can be applied in order to break the anonymity of a possible pederast. And unfortunately, contents in Freenet, what we see in Freenet, is full of this sort of rubbish, people uploading child pornography, and with things like Freenet, this is very difficult to censor, and so we have to make efforts in this direction. Not so much with TOR now. The services related to arms dealing, etc., but not so often. Many people are moving to Freenet in order to share illegal contents. And well,
pues esto es todo.
And that is all. Thank you very much for your attention. Thank you.
¿Tenéis alguna pregunta?
Any questions? No? Well, thank you.